Today, we're going to look at graphing exponential and logarithmic functions. First of all, what is an exponential function? An exponential function is where the exponent is a variable. So we haven't seen that before. In the exponent, it's now a variable. We're used to seeing numbers up there, but now the exponent is a variable. And that's what makes these exponential. Also, we're going to look at some applications on another day and whether we're looking at exponential growth or exponential decay. Going to have a little fun with some special models. First of all, let's start off by graphing y equals 2 to the x. I suggest that we start off by making a table. So if you plug in 2 to the negative 3, that's going to be 1 over 2 to the third, which is 1/8. And if you continue to plug the values in, you can easily populate the table. Remember, anything to the 0 power equals 1. 2 to the first power is 2. 2 squared is 4. 2 to the third is 8. So now we can estimate these values. That's an important point right there, 0, 1. You're going to notice that lots of graphs go through that point. And it's a nice smooth curve that starts to shoot up really fast. And this is a characteristic of exponential functions. They start off gradual and then zoom. Because notice if we put in 4, 2 to the fourth power is 16. So zoom really, really fast. Okay. I want to introduce you to a word. I'm not sure if you know it, but the word is called asymptote. This graph has an asymptote. And an asymptote, we usually put it dotted on the graph. And it's a limit line. It means that the graph gets closer and closer and closer, but it actually never touches that line. So I say an asymptote is like a first date. You get close, but don't touch. Okay, let's look at the next graph. Now we have 1/2 to the x power. So if we plug in negative 3, the negative sign gives us the reciprocal, and now that's just 8. 2 times 2 times 2. And if we continue and plug in our values, that'll give us the reciprocal again, and you'll start to fill in the table. Again, anything to the 0 power. What happens if we punch in 1? Well, that's just 1/2. What happens if we put in 2? We distribute that exponent, so we get 1 over 4. And 1 over 8. And as we graph these points, 2, 3, 4, 5, 6, 7, 8, we'll see that these numbers are very familiar. As a matter of fact, this mirrors the last graph that we just did. And we still have an asymptote right on this line again. By the way, the equation of this asymptote is y equals 0. Notice it's perpendicular to the y-axis at 0. Let's go ahead and connect this graph. And notice that it's super similar to the last graph. This graph from example 1, if you read from left to right, increases. So we see we have growth. This graph starts high and then it decreases. Okay, and right now we have the coronavirus and we see that it grew exponentially, like example 1. When you take antibiotics, it models the decay, and we see that a value would decay as you have less and less and less. This graph shows something cutting in half. Example 1 shows something that's doubling. We'll talk more about that later. Now, let's look at a logarithmic graph. Notice that I did not populate this graph. And the reason that I did not populate it is because I want us to use what we know about inverses. First of all, if we find the inverse of this, let's recall that we switch x and y. And now, if we want to get y by itself, all we do is rewrite this in exponential form. So that would be a base of 2, an exponent of x, and that equals y. So we know that this and this are inverse functions. And what we learned before is that an easy way to graph something is by switching the table, switching the x's and y's. We just made a table in example 1 for this one, and I'll just write some of the values down for you. That was 1/8, 1/4, 1/2, 1, 2, 4, and 8. And so now what we can do is we can take the x values and make them the y values. And now the y values become our x values. And this is just a sneaky little way to do this graph. Remember, if we were to graph them both, they would be a reflection in this line. So remember, if we were to graph both, there would be a reflection. But right now, let's stick to the task at hand. Over 1/8 down 3, over 1/4 down 2, and I'm just approximating these fractions. 1, 0, that's an important point. 2, 1, 4, 2, and 8, 3. And we connect those points as smooth as possible. And notice we have an asymptote again. This time, the limit line is on the y-axis. And the equation of this is x equals 0. It's perpendicular to the x-axis at 0. So we have a limit line again. And hopefully you do see the similarity to example 1 when the graph was going through like that. So you can see that we do have that reflection or in that line y equals x. Let's graph y equals 7 to the x power. Again, we have an exponential function, but you know, Miss Adams, I like a shortcut, okay? I'm going to show you an easy way to approximate this. We know this graph is similar to y equals 2 to the x, but what's the difference? Well, if we were to plug in 0, 7 to the 0 is still 1. And if we were to plug in 1, this graph would go to 7. 1, 2, 3, 4, 5, 6, 7. Oops. No point here. So I just made a little table in my head. Oops. And the table I made in my head was -1, 0, and 1. Because I know the shape of this graph. Okay? So if I were graphing y equals 3 to the x, as a matter of fact, let me do that in a different color. I would just do a third, 1, and 1 would go to 3. So notice the base gives me a nice little point of 1, 3. This one, I knew I could just go to 1, 7. Okay, so you're going to see that it's pretty easy. What would be my next point if I were graphing this one? Well, 3 to the second power is 9. So 2 would go to 9. So I want you to start getting used to what's going on. Okay. If I'm graphing log base 5 of x, I know I'm going through this point, and I'm going to go over 5 up 1. The next point would be over 25 up 2, because log base 5 of 25 is 2. I know there's an asymptote, and I'm just going to fake the rest. Okay, so I just know the basic shape of these graphs. Now, I'd like to introduce you to Euler's number. Notice that it's pronounced Euler, not Euler or anything like that. And Leonardo Euler was a famous mathematician, has lots of different things that he discovered, but this is probably his most famous. Euler's number is approximately 2.72. And it's also been called the natural number. And it's what we call a transcendental number. It has a higher meaning. Just like pi is the ratio of the circumference to the diameter, Euler's number is an infinite series. I don't even know why I'm telling you this, because I haven't even taught you what a series is yet, but we will get to it. So it's an infinite series from 0 to infinity of 1 over n factorial, but you'll actually learn that before the year is over. It's really easy, so don't be afraid. Also, I want you to know Euler's number is somewhere between 2 and 3, but closer to 3. So if I were to ask you to graph y equals e to the x, well, it goes through 1 and about 2.7. You know, you could fake the rest because you know what it looks like. And if I were asked you to graph, we need to talk about this. If I were to ask you to graph y equals log base e of x, then we would put a point here at 1, and then we would go over about 2.7 and go up like that. Now, I have something to tell you about log base e. And we need to make sure we know that log base e, and make sure you highlight this, is the natural log. I mentioned it in the last lesson, and it's not IN or 1N, it's LN for natural log. I don't know why it's backwards. It's probably Greek or something. I don't know. So these mean the samey thingy. Okay. Let's move on to example 5. So the natural log of 1, what might that be? Well, what I like to do is rewrite ln as log base e. And it just gives me a base and something to look at that I can understand. So e to what power equals 1? Well, anything to the 0 power equals 1, so that's 0. Now, what is the natural log of e? No calculator needed here. I'm going to change ln to log base e of e. So e to what power equals e? The first power. So this just equals 1. Alrighty. Now what I want to tell you about e is that it's a number, but it behaves like a variable. Okay? E is a number, but behaves like a variable at times. Alrighty, let's simplify this part A right here. I want you to first just look at the number part and reduce that. Let's see, 3 goes into both of those. 3 goes into 27 9 times and into 12 4 times. Now, this is what I mean when I say you can treat it like a variable. Just subtract exponents. So 7 minus 3 is 4. And that's a good answer right there. Now, what do we know when numbers have the same base? What can we do with the exponents? We add them. So that's x plus 2x plus 5. So that's e to the 3x plus 5. We don't know what x is, so we're done. That's no different than if we had x squared times x to the 5th. We would have just done 2 plus 5 is 7. Now what about this one? The index is 2, so 6 divided by 2 is 3. Do we need absolute value bars? Even, odd? One might say yes, but I say e is a positive number. So the answer is just e to the 3rd.